Hello and welcome to our webinar, Architecture-Driven Development for Embedded Systems. My name is Thomas Schütz from Protos. So, what is it all about? Why do we place the architecture in the development into the center of our complete development process? Because we want to master software complexity. The only real problem we have to solve is complexity. If it's not complex, it's not a problem. So whatever problem you have, if it's not complex, it's not hard to cope with. So let's focus on mastering software complexity, and architecture is an excellent way to cope with complexity. Let's have first a look at the power of abstraction. I have a little example with matches. If you count those matches, most people say it's 30 matches, 40, 50 matches, maybe 100, but we don't really know without really counting them because they're not in an order. It's not easy to count them. So if we bring them into a certain pattern, suddenly you can count them very fast. It's 123 matches. It's the same number, by the way. And what happened here? We brought in an abstraction. We left away, or we rearranged the matches, and we left away the free position of the matches. We brought the position of the matches to a certain pattern. By doing that, we created an abstraction exactly for the purpose to count those matches. So that's also a very important thing. An abstraction always leaves away information and has the purpose to enable to really understand a certain part of the problem. It's not the whole problem, it's a part of the problem you begin to understand. And by that you can divide and conquer the problem and understand each aspect of the problem better. So that's the power of abstraction. A real-world software system looks more like that, with matches. And to prove this to you, I parsed in a medium-sized motor control project, C code, and created a flat UML class diagram out of it. And that's exactly what happens. You do not have an abstraction. A class diagram in itself is not an abstraction. It's just a graphical representation of your code. So a flat model here doesn't help at all. It's a real class diagram. So, but how do we get abstraction into our systems, and how can we handle this a little bit easier? Let's have a look at software development. In the end, you want to create an executable for your microcontroller, for your program. The executable is describes the problem in a way the microcontroller or the processor can execute. But that's not something we can do very well. So we created abstractions like C programs, like higher level programming languages, for example, C, Java, and so on. And as human beings, we already can work on that level. But we still explain step by step what the processor needs to do. It's still a description of the functionality and not of we actually want. One level above, if you create a state machine, for example, that's a much higher level of abstraction. In a state machine, you can describe what you want. In a C program, how it has to be done. And in the executable, how does the processor understand it? So from executable to the C program, you leave away a lot of details that are not interesting for you as a human being. And from the C program to the model, you leave away the how and focus on the what. So you have an abstraction. The problem is, if you want to work on that abstraction level on a state machine, for example, then you need to create a C program or an executable. So a good way to do this is to generate the code from your model and then to compile the C program into an executable. So by that you get abstraction in the one direction and automation in the other. And that's an excellent way to work with model-driven development and tests. So let's have a look at what happens if you put the architecture in the center of the development. In the center, you have an architecture model, structure and behavior of your architecture. In this case, with the programming language or with the modeling language ROOM, real-time object-oriented modeling. So you start with the architecture, usually with the structural architecture, but you also have a behavioral architecture. Then you drill down, you decompose your components, design more structure, more detailed behavior, and you generate the application with a code generator. So now you have a running application. At the other end, you need to test this application. A very good way is first to do software in the loop tests, unit tests, software in the loop tests, component tests, and so on, to make sure that your software components work well. And then for an embedded system to really know that it's working good, eventually you will need a system test or a hardware in the loop system test. And if you put everything into those models, if you place the architecture model in the center, you can attach all those elements to the architecture model and work with one approach. And here, that's continuous integration. Why do I put this continuous integration in the picture? Because there are a lot of things you do not want to do manually. For example, running the test cases, making sure that the test cases are run on every commit, on every software change. So that's why I want continuous integration to take care of the automatable things. So everything we do should be automatable. The method behind this all is ROOM, real-time object-oriented modeling. You can see the book here. It's available at Amazon. That's the standard book for real-time object-oriented modeling. It's been designed for complex embedded systems, telecom systems, avionics systems, and so on, machine controls. And it puts the architecture into the center of development. So it's essentially an architecture language and a methodology around it. It enables the integration with many other tools and methods, because in the architecture, you have always a place to put other technologies, other languages, other tools, and so on. You have a very clearly defined semantics that enable code generation. So if it's formal enough, you can generate code. That's important because you want to automate the code generation, abstraction and automation. And it's very good for concurrent asynchronous real-time systems, because that's what it's been defined for. So it's much more formal than the UML, for example, and much more focused on distributed embedded systems. Let's have a look at the tool chain that gives you the power to work with ROOM. We developed an open source tool chain called eTrice. It's hosted at Eclipse. So under eclipse.org/eTrice, you'll find the tooling. And if you have a look at the process, you always start, or many cases you start to define certain scenarios. So what should happen in your software? Then you define a structural hierarchies. You can define containment hierarchies, layering, and so on. So that's a real architecture language. And within every component, you need behavior. And the normal behavior or behavior description for a ROOM component are state machines. That's, of course, for embedded systems, a very good thing to do. But you can also put in a data flow diagram. You can integrate other tools like Simulink models. If you have a closed loop control, you can put in test cases. We have specialized test description languages. You can put in manual C code or other code. So it's always very important to have different languages for different purposes that are specialized on that. And then you generate the code, you run the application on your target or on your Windows development PC or Linux or whatever. And And then you debug and learn, and you debug on the same abstraction level where you define the architecture and for structure and behavior. And then you iterate and learn. So that's a very, very fast and closed process here. Let's have a look at the language itself. I'm only picking out the most important elements. The basic building blocks for programs for software in Room are the components called actors. They define the structure of a system by creating hierarchies. Here you can see, for example, the XY controller is a hierarchical element, and it contains an X and a Y axis. Over the ports, you can communicate. So the ports have a formal description for the interfaces. So ports are the only interfaces of an actor and define the specific roles in its environment. By that, providing a very, very clear decoupling, a strong decoupling of the elements, which is essential for reuse and for testability, and in general to reduce the complexity. The modeling tool itself is based on textual languages, but we also have graphical languages or graphical editors for that. It's always persistent textual because then you can work with it like with a normal programming language like Java or so. You can make imports, you can build libraries, you can diff, you can merge, you can version control things, work on branches and so on. So it feels on that level more like a high-level programming language, but on a much higher level than abstraction with state machines and components and so on. So now we have the structure of the model, and now we need behavior. The behavior description of Room is our state machines. So every component with its ports can be implemented by using state machines. The state machines have direct access to the ports. So you place the state machines directly inside the components. The state machines themselves can also be hierarchically, like here in the XY running, you have a X and a Y process, or you trigger the X and the Y axis. And again, the base language is a textual language. And on top, we have those editors to make it more convenient to create state machines, for example. So state machines define the dynamic behavior of actors. So, and how does this help? Let's have a look at the most important modeling elements of the language Room. So of the Room features, you have actors, you have containment here, you have layering. So layering is another dimension for hierarchies, very important for more complex systems. You have ports, you have state machines, deployment, so you can separate the logical model from the deployment on a physical system. By that, you can run it anywhere. You can test it on your Windows PC, or on your development PC, on a Linux PC, or on continuous integration, and run the same model on a hardware, on a microcontroller. So those are the most important modeling elements, and they map on certain principles in software development, like abstraction, separation of concerns, simplicity, modularity, very important for coping with complexity. And in the end, what you really want is, or what you have is non-functional requirements, robustness, testability, maintainability, reusability, and so on. And now let's have a look at the specific non-functional requirement. By the way, the functionality in most cases does not drive the complexity, but the non-functional requirements, they drive the complexity. Something like safety, security, and so on, robustness, etc., variant handling, etc. So let's have a look at the testability. How does Room help with testability, for example? Testability, you need, as a principle, separation of concerns. That's something that helps with testability. Encapsulation also helps a lot, and especially modularity helps a lot, because if you have strongly decoupled components, for example, you can test them separately. You can develop them separately and you can test them completely isolated. That's a very good thing to have. And in the end, the room features help with certain principles. For example, the actors and the ports and the containment helps a lot with modularity. So by using those features, in the end, you can solve a lot of non-functional requirements, or they help with non-functional requirements. So let's have a look at how do you get from reality, from a real world problem to a certain model. How does Room help there? Let's have a look at the drawing I got from it was an initial drawing of a designer, of a mechanical engineer that designed a machine control, or a machine production machine for Paritech. That's a medical company. They produce medical equipment, inhalers for your lungs and things like that. So highly safety and security, especially safety critical. And those things here, for example, are cylinders. So that's been just a sketch of an idea here. And those are cylinders, those are sensors, and so on. So what happens is the machine takes a cap and puts it on the inhaler, in this case, and measures everything, that everything is okay. So how did we design the machine control for that? From the mechanical structure, we thought about how could we derive the program structure. And we saw we have a cylinder here, we have a cylinder here, cylinder, a lot of cylinders on that level. So we decided to create a cylinder component. So that's a class. And we created a couple of instances of those classes. So I only want to program a cylinder once, of course. And then we have a more complex element like this here. There's a lot of things attached behind. And here we have a hierarchical component that contains other components like a cylinder, like a sensor, like a conveyor belt, and so on. Because we want to encapsulate, because it's a more complex piece, but I want to handle it at one interface. So now I have a structure with all the elements I need to control the system on this level. And now I need a behavior, because the structure alone does not help me. So I need the behavior. And from the description or from the knowledge, what has to happen? So I have to move out, go down, grab something, and so on. We create a state machine that uses those elements to do exactly what I want. So in this case, that's a substate machine here, in a more complex state machine for a certain process we want to run on those elements. So this can completely done with Room. And in this case, we generate, I don't know, 95% of the resulting C code directly from models. In other cases, for example, if you have more libraries and so on, you might only generate 50, 60, 70%, but it's not so relevant, because the important thing is that you have the architecture under control. If in the elements themselves is manual code, doesn't matter. The important thing that you have the coarse-grained architecture, the modules, and the separation of concerns there. So what else do we do with Room, or can you do with Room? The Room architecture model allows the integration of other tools and methods. So for example, what are the use cases? You want to develop a distributed real-time system. You need to do software in the loop tests. You want to do software in the loop tests, hardware in the loop tests, integration in system tests. You want to do environment simulations to run your software without hardware. That's very good for testing and development, and so on and so on. And the main element we use to integrate all those things is the actor, the component, and the ports. We hide everything behind ports. So if you need a driver, create an actor, put in the driver, make a port, and then you're back in the model on a very abstract level, and you can handle the driver much more efficiently on that level and reuse it and so on. So first of all, you need behavior languages. Room itself has state machines as behavior language. You also can integrate closed loop control systems like we have an old data flow language, but you can also use Simulink, generate the C code, integrate it directly into the components. And of course, any kind of high-level programming language, depending on the code generator we use. For example, you use C or C++ or Java. Then you can, of course, integrate manual code on that level inside the actor, and on the outside, you're again in the model, and you can reuse this part of the C code, for example. The next thing you need to integrate interfaces. For example, low-level bus systems like CAN, LIN, XCP, and so on. For that, we have a couple of bus protocol generators, or we create new ones for new technologies, because we do not want to program a CAN scheduler or something like that. That's something we generate, we integrate into the room actor, and again, you can communicate over CAN in the model. Same with low-level I/O, digital, analog, SPI, so everything you need to really control your system. And again, other protocols like high-level protocols, Modbus, EtherCAT, field bus system, TCP/IP. You can hide all those interfaces behind, or all those implementations behind model-level interfaces. Last but not least, we want the integration of test and verification languages. We have, for example, the test description language, and within generator, it's called Cage. So for case generator, it's just an alternative behavior language, which is much more efficient to create test cases, also combinatorial test cases, and so on. And we also have methods to define interface contracts, so contract-based design, to really construct secure and safe systems. So you do not implement them and test them, but you design them in a way that they are that they can be verified on model level, or automatically can be verified on runtime level, or also during test time. So it's a very constructive way to create robust systems. Now I'm going to show you a little demo. I'm going to dig in right into the development environment. Here we have a room system. The components are called actors. They can have sub-actors, sub-components, and what I want to implement is a traffic light. So let's start a traffic light. I have a little traffic light simulator. This could also be a piece of hardware attached to my microcontroller. In this case, that's a little Java graphic user interface with a TCP/IP server, which listens on port 441. And this graphic user interface I can attach to my software, to my room model. As I said, it could also be controlled by digital, analog outputs, inputs, and so on. So now we want to create this traffic light. I'm going into the traffic light container, and so what do I need first? I need TCP/IP socket. Let's just a second. Let's add a TCP/IP client, because the graphic user interface is the server. So let's call this socket. That's a standard element. That's one of those elements, as I mentioned before, we encapsulate once, and then you have a socket on model level. Then I prepared a little translation between the model and the TCP/IP message. So it's just a model to text conversion, if you will. That's the traffic light interface, TL interface. Let's call this. So as you can see, it already comes with a control port to configure TCP/IP, and with a payload port to send and receive messages over TCP/IP. And the interface is just a protocol interface. So for example, if you want to send something, request for the button active, or if you want to set the pedestrian light to red, we just send the text set pad light red and true or false over the TCP/IP interface. It's just a very, very simple message dispatcher. You create it once and use it forever. And as you can see, I did the separation of concerns here. I distinguished between the payload port and the control port. With a control port, I configured the port, for example, for TCP/IP. The big advantage is if the payload port is separate, I could use also a UART or a SPI or any other protocol and still use the same traffic light interface. I just need to change the configuration. With a UART, you have a baud rate. With a socket, you have a port, for example. So that's an example how you can use ports for separation of concerns. So, and now I want to create the controller itself. So let's just jump to the textual syntax. I prepared an empty traffic light controller. So it's just an empty component. So let's go back to the graphical user interface here, and I'm dragging in the traffic light controller. It's just an empty component. Let's call this controller. Okay, now I have a traffic light controller. Now I need the port to communicate with the interface here. So let's go in there, give it a port. I call this TL. That's of the type traffic light controller, traffic light interface. Okay, so let's go back. Now I have this interface here. I can attach this to the traffic light interface component. So, and that's it. That's the structure. It would already run. It would do nothing, but it would run. And now I need behavior because, of course, I need a behavior for a traffic light. So I open the state machine. At the first state, I would need to connect over TCP/IP with the traffic light itself. So 4441 is the port number of the graphical user interface, in this case of the traffic light. So now I send the connect message and I receive another message, and then I want to set, for example, the traffic light, the car, to red, to green as an initial state, for example. So let's TL dot set car green to true, and TL dot set pad red to false, true, sorry. And yeah, now I connect them and I go to the next step when the traffic light is connected, and then immediately it sets the traffic lights to the right states. So that's it for the first step. Let's open the traffic light itself. I'm going to start the build process and run the traffic light application I just designed. So now it's generating the structure and the behavior of the system as C code. It's compiling it and it's running. So as you can see, it already put the traffic light into the right first state. Now I can send a request, but my application does not react on that because I did not implement it. So let's stop the application again and have a look at what happened inside my model. So for that, we generate sequence diagrams during runtime, and that's exactly what happened now. The controller connected, and in the end, the controller set the car green and the pad red, sent it over the socket, and in the end, I press the request button. I already can see this here, but there's no reaction because I did not implement it. So that's the first step. Now let's go back to the traffic light controller. Just a second. And now I'm going to cheat a bit. I'm going to throw this out, and I have a prepared traffic light controller. That's the same thing here. So let's just rearrange those a little bit here. So now I have an implemented traffic light controller, which does the complete thing. So I'm going to save it again, and I'm going to build and run it again. And now let's have a look at the functionality here of my traffic light. So it's still building, generating, building, and running. So, and now I press the request button, and as you can see, the traffic light is working. So now I'm going to stop this application again and have a look at what happened on a sequence diagram. And here you can see, oh yeah, there's happening much more because now I have a completely implemented traffic light. So that's the second step now. So now let's assume we want 20 traffic lights. So let's stop this one traffic light and let's start 20 traffic lights. Why do I want to do this? Because I want to show the scalability of the system. So now I have traffic lights, or I have hundreds of traffic lights or thousands of traffic lights. Doesn't matter at all. And now I want to control them. So let's go into the application structure again. Here we have a controller, the interface, and the socket. So I could give them a multiplicity now and say, okay, I have 20 controllers and 20 interfaces and so on. But I don't want to do this 3 times. It just doesn't scale. So that's why I move one level up. And they're all inside the traffic light container. So I edit the reference here and I create 20 traffic light containers. I save this and I restart again the application. And now I'm going to run 20 traffic lights. So you see, they are online now. And now I have 20 traffic light controllers running in parallel. If I want to coordinate them, shut them down at the same time, start them up in the morning and so on, I give them a port. I create one other component with a replicated port with a multiplicity, and then I can control 100 traffic lights or complete city in this case. Yeah. So that's how you can scale. It's just a little example of how you can scale this kind of application. And now I want to test this kind of application. So let's again have a look at let's stop the traffic lights. And now we want to create test cases. In order to do this, I just activate a test container. It's just an empty test container. So I'm just replaced the application container with a test container. And in the test container, I have an empty test case. And now I drag in my component I want to test. I have the traffic light controller. That's the one I implemented. Let's call this controller. And of course, the traffic light controller has this interface here. And I want to test the functionality of the traffic light controller. So I connect the interfaces here. And again, this is just another instance of the state machine I just created. So essentially, a test case is just a reuse of a component. That's why it's so easy to do with Room, because the components are always decoupled, so you can easily isolate and test them at the interface. So now let's have a look at the test case. We could do a state machine for a test case, but there's a much more efficient way to create test cases, and that's why we created a separate language. It's called Cage. It's just another behavioral language for a component, which is specialized for creating test cases. So now I have an empty smoke test here. Let's create the first step for the test case. I want to connect. Let's create an action. I have the interface already, traffic light interface, and I want to send a connected back when I connect, because I expect a connect and I send back a connected. So The next step would be I want to check a reaction. I expect, for example, again from the traffic light interface, I expect a set car green, and I expect a true here. So I can tell exactly what message in return I expect. Oh, true. And let's do a second step. And in the second step, I want to send a request. Send request to my send request. And so I create an action, and this action sends a request over the traffic light interface. So I do exactly what I've done before with the graphical user interface. I do by sending a press button. And now, of course, I have to add the 2 steps to my smoke test. Yeah, and that's it so far. Now I need to build and run the application again. Usually it's another application with the test case. I don't run it in the production application usually, but in this case it's the same application. I just now trigger the test case from the outside. I run the test case from the outside, and here you can see there's an error, count on 0. So the test case already ran. So now, what happened really in my test? That's the interesting thing. Because it fails, I need to know this. So let's have a look at the traces. We build a sequence diagram, and here you see exactly. I sent the connected. I got back set car red, set car yellow, set car green, and that's the one I expected. And then I sent the request button, and so on and so on. So that's a test report of the system that actually worked. And if it does not work, for example, if an expect fails here, I click on the button and I go back to the place where it actually failed. Good. So that's the demo so far. Let's wrap this up. Now I've shown you how you can develop the architecture, generate the code, run software in the loop test all in one model. You can now continue with the same model to run hardware in the loop test. So you take the test cases, put them on a hardware in the loop test system. Of course, you need a hardware for that. In this case, our mini hill, for example, can also be other hardware you use for testing. In this case, the application runs on this processor and the hardware in the loop test case on this processor, both generated in this case with eTrice and with those models I've shown you before. And in the end, you develop both sides with the same tooling. You develop simulation, test models, and so on. Model-based, you generate, compile, and flash the test cases and the environment simulations to the test system. On that side runs your system under test. Then we create the logs by running the test cases. We transform it into diagrams. Again, you want to see the results on the same level of abstraction you log or you develop. A text log is not very useful for analyzing. So you learn and iterate. Something special, we also can generate combinatorial test cases from models. So for example, from a very concise, very small description of the expected black box behavior as a contract, we can generate lots of test cases that try to break the system or try to prove certain aspects of your system. Those are things you can not do really good with manual test cases. So that's already shows a lot of the power of model-based development. So that's it so far. I hope you enjoyed the webinar, and if you have any questions, don't hesitate to contact me. You see my email here. Hope you enjoyed it and have a nice day. Bye-bye.